Good morning, everybody. I'm Bart Bijnens, one of the researchers here from the department, and it's my pleasure to introduce Miguel González Ballester. He's a computer scientist from somewhere down Valencia. It's like, but I think, as you can see, both in his career and the work that he's doing, he's, to me, a truly versatile biomedical engineer in all the aspects that come with it. So he did a PhD in Oxford, then went to Japan, to find a wife, no, more or less. And where he worked in the industry in Toshiba. Then he came back first to Inria as a researcher in France, then a researcher in Bern, and then he came back to Barcelona to work in a company, a spin-off company. And then later on, now about 10 years ago, I think, he became an ICREA research professor here in the department. So it's like one of these kind of unique kind of career path going through universities, companies, spin-offs, large companies, and different types. So if you're a young researcher that wants to make a career, I think this is quite interesting. You see all the aspects, and you see that then also in his research, which is both fundamental as well as applied, and always looking at the application, either industrial or clinically. And even now, he's kind of trying to do things at the edge, partially for fun, but partially because it might be the future. And so he's talking a little bit about quantum computing and how it might be useful in the healthcare setting. Miguel.
Thanks very much for the introduction, for the very kind introduction. And thanks for coming at this time for the first session. So I always like to start the presentation spending a few seconds or minutes on the title, instead of passing very quickly, because I think it's important to frame well what I'm going to talk about. So you see the title is Quantum Generative Models for Healthcare. Okay, so for healthcare is kind of self-explanatory, right? Generative models, and that would be the first part of my talk, will be without the quantum part. It will be about why the hell would we want to study generative models for healthcare, right? And then the final part, or the second, let's say, half of the presentation, will be getting into the quantum part. So what is quantum computing? What things have we done? And basically, the way I structured it is I will show 3 of our projects on non-quantum generative models for healthcare, and then 3 projects that are ongoing on quantum computing for healthcare. There is another part in the slide there, and it's my name. So I will very quickly go through what already Bart said, because I thought it's kind of interesting for summer school and for people that are thinking about what to do with their lives. Of course, you don't have to take my advice at all. No? But yeah, so I did before the PhD, I was in Jaume I University in Castelló. Yeah? And then I joined this research group in the University of Oxford, in the robotics group. It was the computer vision, well, the medical computer vision group, right? And I was working with Mike Brady, so Sir Michael Brady, and Andrew Zisserman, who on top of being in this group, he was also, or he is still the leader of the visual geometry group, which is the VGG. And you have probably used the VGG nets, yeah, VGG 16, VGG whatever. Yeah. And this guy is really versatile. So he was a big guy in very solid mathematical things like projective invariance, things like that. So inferring projective geometry from just one image, things like that. And then he kind of converted himself into a leader in deep learning. And he was one of the pioneers, really, on very deep neural networks, all the work on deep neural networks. So some of his papers are some of the most cited in the world. Right? And on top of being in Oxford, he's also in DeepMind in Google. So this was the type of things I was doing. That was last millennium. So it was from 1996 to nearly, well, about 2000. Working on active shape models. And you see already the type of things that I was doing. So you start from some shape, some ellipse here, and you pose some optimization problem that is constrained by some physical constraints, right? That activates, let's say, this surface to deform, to try to meet the constraints, these physical constraints, and at the same time to try to adjust to the information that is in the image. Right? So in the end, it's deforming, deforming, deforming until you get the shape of the brain. Right? This is what was known as active shape models. Another thing that I worked when I was there, and I have been keeping working through the years, is the idea of uncertainty quantification and uncertainty propagation. So you can have something like this, you can estimate the surface, but how certain are you about this? How much can you trust the bounds that you're computing, right? So I started with doing these sort of things that are like a bit of a sandwich, right? You have two surfaces that encompass, let's say, the real location of the surface, and then try to estimate what is inside here. So doing a mixture model, try to see what is the imaging process of the MRI, and do things like a partial volume effect, it's called. So estimating what is the proportion of each tissue within each voxel, things like that, right? So to reduce the width of the confidence bounds. After that, like Bart said, I went to Japan. I didn't know what to do with my life, so I said, well, took a mappa mundi. I said, well, okay. So I went there, and apart from meeting my wife, Yasuko, so I also did some work in Toshiba, so more closer to the physics of MRI, so closer to the acquisition, right? And this has been taken through, and now Toshiba has been bought some years ago by Canon, so now it's Canon Medical. But yeah, we were in this place. It's the province that is below Fukushima, so it's about not too far from Tokyo by fast train, and I was there for a couple of years. It was quite interesting. Then I went back to Europe. I got a position in INRIA. INRIA is a public research center in France, focused on computer science and robotics. And there's this group where I was, where we were working on image segmentation, image registration, statistical shape models. I started getting interested also in surgery, so surgical simulation, surgical navigation, things like that, and on how to simulate physics inside these computational models. Then I went to Switzerland, so I was there for about 5 years, where we had a group, a pretty large group, that was embedded within the medical faculty, which itself is quite a challenge, because you are kind of the freaky guys that are engineers within the medical faculty. So super interesting, because you have access to a lot of data, a lot of time from the doctors, and access to the operating rooms and things like that. But at the same time, things like promoting your career and everything, you're competing with different types of animals. Huh? So the experience was very interesting. But yeah, I got to a point where I had a certain age, I had a son and everything, and we were thinking, okay, do I stay in Switzerland forever and have a petit Suisse, or do I want my son to grow here? So I was lucky that I was in contact with the president of a company called Alma, that maybe some of you know. Alma is a startup, so not really a spin-off, it's a startup that was created from the interest of a surgeon that wanted to see if it's possible to plan and simulate his surgeries, right? So he's a plastic surgeon, and he wanted to see if it's possible to simulate, to predict, and do things, right? So hands-on. They teamed together, did a group, and the company is still alive. It has its ups and downs, like all the companies during the crisis, but has been active for many years. They do most of the radiology viewers that are around. So if you go to hospital clinic, or if you go to the surgical viewers that Telefonica uses for teleradiology, things like that, there's technology from these guys without the logo of Alma, of course. So it's kind of sold as OEM. So we were about 20-something, up to 30 people. But at some point, we were covering more countries than the company had. So it was quite an extreme case. And then since about 10 years ago, I joined UPF. I was super lucky to get one of these career positions. And since then, I've been working in this group, okay? So we are a research unit, as most of you know, about 100 people or something like that, up to the level of PhD students. This is the set of PIs in the group. And for people that are from here, you know all of them, because you've been having lectures with them. And we cover a very broad spectrum of things, yeah, from signal processing, image processing, physiological modeling, medical devices, etc., right? So I will start from what I said, yeah? So quantum generative models, but let's start from some examples of projects on generative models for healthcare you've all seen a lot of things on generative AI and things like that, and you know that it can be used to generate nonsense things, yeah, funny images, funny videos, things like that. But first, we should think about what we mean by generative AI or generative models, right? So what would you think is a generative model in this context? Anyone? You.
Me. That's well, a generative model is a model that decides then to generate something based on previous learning. Yeah. So I'm making I don't have a Wikipedia definition in my mind.
Okay.
But as I would make an analogy with generative AI, so for me a generative model as something that can generate new contents, so based on few inputs, so enhanced contents based on few inputs, according to probably a previous learning process. So.
Okay, thank you. So here there are several things, right? So one is from some data, right? The concept of machine learning, right? So you have some data, some example data, and you learn a model, okay? So you can see this as fitting some sort of distribution, right? So if you have a lot of data and you fit a Gaussian to it, yeah, you compute the mean and the standard deviation, that's a model, okay? Is it a generative model? Yeah, you can sample the Gaussian, right? So you can drive new instances. So in a very broad sense, that's already a generative model. But you also mentioned something about conditioning, about like saying, well, generate samples, but based on some constraints, right? And that's also important. I see Oscar wants to jump also on the, yeah.
Every model is generative, no?
In a sense, by definition, yeah. Okay, so that's a bit where I want to frame things, yeah? And of course, as you know, there are a number of very powerful methods around that have been in the forefront recently, like generative adversarial networks, variational autoencoders, these noise diffusion models, things like that, right? So what I'll show now is a couple of projects on generative models for healthcare, just to see why we would be interested in this space. And then for the second part, I will jump more on the quantum side, right? So the first one, since Oscar talked, is a project that Oscar and I directed, but all the work was done by Iram, who was a PhD student in our group. So the title of this work is ATRI-VAE, okay? So attribute-based interpretable representations of medical images with variational autoencoders. And so the basic tool for this is variational autoencoders, which is a type of generative model. And I will explain a little bit how this works. Here's the reference, just to see from where this work comes. But what's a variational autoencoder? Okay, I don't know. Some of you probably studied it or know it or work on this space. Some other maybe not. First of all, it's an autoencoder. Okay? An autoencoder is a neural network, okay, that takes as input something, okay, let's say an image of this guy with a beard, and let's say that you have a vector, okay, you take this image and you encode it as a very long vector. So you take all the voxels, all the pixels of this image, and you put them one after another, so you have a very, very long vector, okay? This very, very long vector can be put as inputs to a neural network. So you have this input in the first layer, and then you have different layers that are doing some computation. And you know neural networks, what they do is take the information of one neuron, the information of another, and combine them with some formula, with some weight, some linear transformation, basically, and then have an activation function that is where the nonlinearity comes. Okay. So what you can do is take the input, and as you pass through the layers, reduce the size of this vector. Okay, so you have these pooling operations and things like that in the end are compressing your representation. Okay, so it's a kind of dimensionality reduction type of thing, right? And you do this, you reduce the size until you get to an intermediate level, a final level, where you have a shorter representation of the image. Okay? And it's called an autoencoder because it's trying to compute this automatically. So it gets your image, and then it computes a lower dimensional representation of this same image. Okay? That will be the encoder part, the first part of it. And the second part will be the decoder. So once you have this, you have also something in the other direction, right, that can generate again the image. Okay? Now, there are more things here in the middle. So we see that this doesn't have just one thing. So if you ignore this part here, you would have what I'm saying. Yeah? So you have something that reduces dimensionality, ends with some sort of latent space here that has few dimensions, and then grows again, right? But here you see that it has something that represents the mean and the variance. Okay? And this is the difference between a standard autoencoder and a variational autoencoder. Okay? So the idea is that you learn not only the distribution in a sort of deterministic way, you're trying to learn what is the probability distribution in this latent space. So in the end, you're generating a PDF, a probability density function, of what are the likely representations, okay, that generate data that fit the training data that you gave the network. Okay? So here there are a number of things that happen, like I said, so the encoder, right, the variance and the mean. So implicitly you're assuming that your distribution follows some sort of Gaussian. From here, what happens is that you sample a particular value to then do the decoding to generate new images. Okay? And I will go a bit faster through this, but yeah, basically you train it with a loss that is a reconstruction loss that is basically telling it, I have an input, I make it go through all this stuff, yeah? And at the end, if I go through this input and I go through this, I should get exactly the same image. So you have a loss that is comparing these to say, okay, the reconstruction is good, right? And then you have another loss that is trying to enforce this idea here that the latent representation should follow a Gaussian with mean 0 and standard deviation 1 in this case. And you do this by optimizing a distributional distance, right? A distance between probability density functions, in particular the KL divergence, which is not the Kelvin-Lorentz, but the Kullbaum-Leibler divergence. Okay. Then what else were we interested in this project? In particular, we were interested in learning representations that were interpretable. Okay, so from here you can already generate things, right? I will maybe skip this because it's not so important. But in the end, what we wanted to do is a system that was able to do this encoding, decoding, and at the same time be able to somehow be interpretable. So to say, okay, why did you generate this image? Or if you give me an image of a heart, can I manipulate it? Can I say, okay, generate an image like this one of this patient, but simulating that the myocardium is thicker, right? Things like that. And this has several steps. So basically, just focus on this center part here, okay, for the time being. You have the input of the image. You have the encoder, like before. You have the mean and the standard deviation. From here, you sample, okay, set. And you have the decoder, okay. Things that we touched upon in this system. So we had also a classifier here to try to learn from this low dimensional representation if this heart is healthy, if it has some pathology, things like that. We also incorporated some things to highlight why the network is making some predictions, so to give this sort of activation maps or heat maps, as are known. But the key part was this part of attribute-based regularization, which is where I will focus now in the next slides. Right, so the first element that I mentioned was the classifier, and we were not the first one to do. There's this work of Carlo Biffi and some others that tried to incorporate this sort of classifiers within variational autoencoders, and they showed that it has a number of advantages, okay, to include this multi-layer perceptron in the latent space. It's a prediction network. It helps also the stability of the network when you're training. Okay. For the gradient maps were based on several works that are already existing, you know, most of GradCams and things like that, that look at the way the network is being trained. look back at the gradients of the different layers of the network to see what is driving the final decision to classify an image as healthy or unhealthy, right? And where the gradients are high, basically, it's where the information weighs more for the final decision. So you can sort of visualize this in the native space of the input image. So to say, okay, this part of the image is the one that told me that this is a 5 and not a 1, right? And this is why it's highlighted here. Yeah. These sort of things. The thing of attribute regularization was an idea that also it wasn't Oscar and I solely that came with the idea, but based on ongoing work of, for example, this paper of Patty. And the idea was to incorporate, let's say, clinical or intuitive concepts into the learning process. Okay? So you have this image, you train, encoder, whatever, but all this is kind of blind, right? But in the end, when you want to explain to a doctor or you want to discuss this image, you have a number of intuitive concepts like whatever myocardial thickness, like whether the patient has certain weight or things like that. And you want to somehow tell the method to take this into account, right? And this is what we're doing with this method. Okay, so I will now show how it works in the formulas in the next slides. But it works on any type of attributes, either continuous or discrete. It already acts in the training stage, so it's not something post hoc, like many interpretable deep learning methods that are based on, okay, once you're trained, you do a lot of things to see why the hell it took this decision. And yeah, that's it. So I'll go this way. So in the end, okay, the explanation of the attribute will come now. In the end, what we have in the loss of the method was this. So we have the input image. We have this autoencoder, variational autoencoder. Okay. There's the reconstruction loss, as usual. Okay. So the input image, when you train, should generate an output image that looks like the input image. There's the callback library divergence here loss to enforce that the latent space is somehow following a Gaussian distribution. Okay. You have also the MLP loss. So when you train, you know that these cases are healthy or not. So you input this to train this multilayer perceptron as well. Okay. And finally, the attribute regularization loss, which is what I was saying. So in this case, the way it works is that you take mini batches. So you take subsets of the data, small subsets, yeah? And you do like a ranking. So if you have an attribute, for example, myocardial thickness or volume or whatever, you take the mini batches and you sort them. Okay, this is higher, this is lower, etc. And then the loss is enforcing that this order is kept. So it's not enforcing absolute values of this because the scales are very different when you're comparing volumes, diameters, age, whether a patient smokes or not, things like that, right? So that's a bit how it works. Okay, so, and at testing, when you have a new image, what happens is you put a new image, it does this, it gives you a prediction whether this image is healthy or not, right? It gives you the possibility also to do what we call attribute scanning, because when you input a new image, you get a representation of this image, okay? So you get a latent vector here. But by training of this attribute regularization thing, we are enforcing that some elements of this latent vector correspond directly to some interpretable attributes. So for example, the first element corresponds to the volume, the second element corresponds to the age, etc., right? So we can manipulate. We can take the image and say, okay, simulate this same image, but with an older patient, or simulate this image with a thicker myocardium, things like that. Okay. And then, of course, the explanation maps that I was talking about. Okay. And this I will jump because it's for the sake of time. So we applied this to a number of cases, well, implemented it in PyTorch, etc. And these are just some visual examples. So we see here, for example, when we get the input image, okay, we encode it. This is the same image, okay? This is the input image. And this is showing a bit what we meant by attribute scanning. So we take the dimension of the latent space, the element of that vector that corresponds to the volume of the left ventricle, and we manipulate it. We increase it artificially, right? And then we pass it through the decoder to generate a new image. Okay? And this new image will look like the input image, but with a thicker myocardium, with a more volume or less volume, right? And you can see here the contours and a bit that actually is doing what it's asked to. Okay. We have these activation maps as well that I mentioned, and other aspects that we studied also to manipulate. Okay. We tested also on the classifier, etc. Yeah, I just passed because I want to show the other examples as well, and then you're here for the quantum, so I want to pass this a bit. Like I said, so this method allows for attribute-specific interpretation, synthetic data generation, and classification. In this case, was applied to cardiovascular. Of course, it can be applied to anything. Generates interpretable representations where different types of attributes, for example, clinical attributes or clinical measurements, measures of shape, or things like from radiomics, texture measures, things like that, can be automatically individually encoded in a given element of the resulting latent space. Okay? So you can manipulate it with a slider, let's say, and generate new images. Okay? Right. So that was the first example of things that we do with generative models in the group. I will show a second example. This time is work that I did with Gemma. Okay? So we try to work together in the group, like you see. This was the PhD thesis of Xavi Rafael, okay, who was working in EureCAD and at the same time doing the PhD here. And now he's working in a company called Kibim. And his work was on uncertainty-aware. Like you saw at the beginning, uncertainty has always been something that is interesting for me. Hierarchical probabilistic network for early prediction, quantification, and segmentation of pulmonary tumor growth. Okay? So here we're focusing on lung cancer, okay? Pulmonary tumors, right? And what we want to do is to predict for a patient the likely evolution of a nodule, okay? That's a bit the idea. So how to leverage some sort of generative model or some sort of model that we build on the data to learn from the images, learn from the patients at different stages of disease, right? To be able to predict for a particular patient, 6 months from now, 1 year from now, 2 years from now, what is the likely evolution of a particular nodule, and generate synthetic images showing the likely evolution of the tumor. Okay. For this, very quickly, what I said, so to try to predict future growth of a nodule, ideally to be able to do more targeted screening strategies or more targeted treatment planning, more effective screening, so to identify patients that should have a better, let's say, a closer follow-up. And, well, the idea of tumor growth forecasting in itself is an interesting scientific topic. Traditionally, this tumor growth has been modeled in many ways. Yeah, let's say the most popular one is this sort of reaction diffusion models where you have a formula that is taking into account cell proliferation, tumor invasion, whether it metastasizes, etc. These are interesting models, but usually, of course, they are very simplified in the number of aspects that they take into account, and particularly also on the personalization of the prediction. Because in the end, you take these kind of standard models, you take into account the intensities of the image if you want, but, well, that's not super personalized. There are a few more recent works that are based on deep learning, like this one, okay? This is deterministic, so it doesn't take into account the uncertainty. What I mean in uncertainty is that we don't want just one prediction. We want to predict a distribution of likely evolutions of this tumor in the future, right? So something where you can sample and you can compute, for example, confidence bounds and things like that. Yeah? So this wasn't doing this. It is very interesting work. It had, it was based on a number of cases. They took 3D images of lung CTs. It's based on 2 units, as most of you probably know this architecture. What we said, yeah, the final performance when evaluated was not super fantastic, but the problem is very challenging. And what we said about the not taking into account the uncertainty. This is also another very interesting work, okay? It was based on a combination of CNNs and recurrent neural networks to take into account the temporal evolution, right? Some limitations that we identified, well, the study was very limited. It was to about 10 patients. For input, necessarily, you must have already temporal images of this image, which is not something that in most cases have. Yeah? So we want to train the model to predict, but we don't want to enforce having temporal follow-up data already, right? We want to be able to predict from one single time point. And also, their task was very focused on a specific thing. I think, if I'm not wrong, that it was related to radiotherapy planning. So what they wanted to predict was the evolution in a very short time span, so in a few weeks, right? And we want to go farther, right? Other methods, like I said, well, again, so this method was not taking into account the variable of how far away you want to predict, right? It was just generating one. Okay, it will follow like this, but doesn't tell you how long it will take. Yeah. The same thing about the cohort, etc. This one, maybe I will just jump all this because it's just prior work that is relevant. And identifying this subset of methods, we noticed, well, this is very interesting, but none of these methods take into account things like inter-observer variability, which is something that, I mean, we were working with Valdebron Hospital, and we were very lucky to have the radiologist involved. And so for every patient, we have several annotators, and that's a source of variability, of uncertainty that is very interesting to consider. They were not taking into account uncertainty in the prediction, which is something that we wanted to do. And this was what we worked on, right? So this was the work of Xavi Rafael. So he proposed this architecture. It's based on two paired U-nets, well, U ResNets, that are trying to model, on the one hand, the appearance, so from the tumor go to the segmentation, let's say. On the other hand, the temporal evolution, right? And they allow, well, they have a number of things. I'm not going to go into the full detail of explaining this diagram, but for example, you can put as input and directly into the latent space of the unit, take into account the temporal difference that you want to predict on. So that's an input that you can say, okay, I want to predict 6 months from now or 2 years from now, whatever. And then the decoder will generate different images depending on what you input, right? It had some, well, whatever, soft attention and things like that that were hot at the time. Well, it's still quite hot because transformers are a thing still. Yeah, well, it's based on variational optimization, and we had to modify a bit the reconstruction laws, etc. So again, for the sake of time, I'm not getting into the details. I just want you to get the basic idea of this. From this method, you can generate a distribution of images. So you can sample. Yeah? You can generate a lot of images of how likely this tumor will be in the future, and then compute things like the mean likely diameter, the standard deviation, some sort of confidence bounds, things like that. Okay, like I said, so we had some images from Valdebron that were annotated by different radiologists. We analyzed variability in the cohort, things like that. We compared with different architectures that we had to actually modify a bit because they were not taken into account. I mean, this particular application of temporal prediction, even though there was some previous work, there was not so much there. So we compared, for example, with a GAN type of architecture, so a generative adversarial network, where you have a generator, a discriminator, these things. And as in most papers nowadays, you have to say that your method is best than everything else. But just to give some examples, yeah, this would be a nodule for which we had the ground truth, let's say. So we had time 0, okay, and the contour at time 0. And we had time 1, right? And we were predicting, okay, so that's the predicted mask, let's say. So the predicted segmentation at time 1 overlaid on the image on the real image at time 1. So you can see, okay, the input is this one, and the output would be this contour that actually, when you get the image at time 1, we verified that it looks quite similar to what it was predicting. Yeah? And you have like confidence bounds to see where the uncertainty is, so where the bounds are probably not so accurate, or there can be some differences, right? And some others that were working worse, yeah, because, well, whatever, they were, for example, close to the border of the lungs, and this made it more difficult to predict that the shape would take this type of way instead of the predicted one that was like this. So it kind of correctly identified that the tumor was going to grow, but it failed to take into account that the wall of the lung is there, so the shape would be different. Right? Okay. So anyway, this uncertainty-aware hierarchical probabilistic network to propose or to predict likely growth. Right? Now, for the sake of time, the third example, I'm going to go even faster. This is the PhD thesis of Mireia Macias, right? That is co-supervised by Gemma and me also. As we speak, she's preparing the presentation for the PhD defense that will be in a few weeks. And this work in particular is part of this thesis, predicting structural brain trajectories using discrete optimal transport normalizing flows. Okay, that's a bit of a mouthful. If you go from the end to the beginning, normalizing flows is a type of generative model. Okay, so it's maybe not as popular as diffusion models and GANs, etc., but it's a strategy to do generative AI. Okay. Optimal transport, some of you may know. Okay, so it's a mathematical formulation to go from one statistical distribution to another, meeting certain constraints. Okay. Discrete, okay, not continuous. And predicting structural brain trajectories. Okay, so the idea of this work, okay, was to focus on this problem here, where we have a patient, okay, we have a brain image at, for example, 30 years, and we want to model what is the trajectory. We want to kind of generate images at the different ages of evolution of the patient. Okay. So for this, again, there is some prior work. I will jump quickly because I just want to follow a bit on the method itself. These people that have tried to do things similarly for GANs, etc. Okay. But I want to explain the concept of normalizing flows. Okay. So normalizing flows are a methodology that was quite prominent a few years ago. It's still there. It has a number of very interesting properties, right? That takes a distribution of the data. Okay. So you have your initial data that follows a certain distribution, right? And it's doing a set of small invertible transformations, right, that convert your distribution of the data into a simpler distribution, for example, a Gaussian. Okay? So you can imagine if you have a very complex distribution of your data, because you have subjects with very different characteristics. If you do this, in the end, you have a sort of latent space that is very simple. It's a Gaussian. You can sample from it and then go back to the original space to generate real images. Okay. How does it compare with other generative models? Well, first of all, like I said, it's invertible, so it's totally bijective. You can go from one direction to the other. If you compare, for example, with variational autoencoders, it has a explicit computation of the distribution, which variational autoencoders doesn't, because it's based on an optimization based on a lower bound, right? So not on the actual distribution. It has more expressive power, so variational autoencoders are known to generate images that are a bit blurry, so not really as good as the original data. Like we said, for variational autoencoders, but also for GANs, these ones, they compute a PDF. They compute something that you can sample, you can transfer, you can do things, right? Whereas, for example, generative adversarial networks, they have a generator and a discriminator, and you train it to do a min-max problem, it's called, so something where they are competing. Okay, so you train the generator, which is a neural network, to generate data that looks like the training data that you gave. Okay, and you train the discriminator to be able to differentiate data, whether it's real data or data generated from the generator, so fake data, right? By game theory, Nash equilibrium, etc., you end up into something that is actually minimizing. It goes in the right direction. So in the end, you have a generator that generates images that are very, very realistic. Okay. And then there's the other one, diffusion models, that are very similar in idea. So diffusion models, basically, you take images and you add noise, okay, noise diffusion models. So you add Gaussian noise, basically. And there is a whole theory that tells you that you can actually train networks that do the inverse process in a way that from noise can generate images that are like the training data. Okay. It's very similar, but not exactly the same. But I will not get into this. Yeah. So I will go very fast. I will get into quantum now. So the optimal transport problem, it was just to say, okay, we don't want to go from the original distribution, for example, data of 20 years old, to a very simple Gaussian distribution. We want to go from the distribution of 20 years to the distribution of, for example, 70. Right? So it's a sort of distribution matching problem, and that's where the optimal transport part happens. Okay. All right. This what I said. Okay, so instead of going to the simple distribution, you go to another distribution. Yeah, and that's where the optimal transport part happens. These are implementation details for normalizing flows with coupling layers and things like that for people that are aware, but maybe it's not so important. Okay, we did studies, we compared the results, etc. But basically, the idea is that from one image of one age, we were able to generate a trajectory, so simulated images of brain growth, right? And that was a bit the idea. Okay. Right, so these are different uses of generative models for medical images, right? And why did I give you all this stuff before going into quantum? Because I get very often comments like, but you know, generative models for AI are useless. No, I mean, why would you want to generate images? No, because some people are saying, no, we will create a generative model to generate synthetic images to enrich our training set. But you have to be careful because you train data, you train a model from your input images, and this model will reflect your input images, right? It will not increase the diversity of your training set. So you may be actually biasing your training strategy by sampling synthetic data from the distribution of the data that you have. I mean, it's probably not going to contribute to have a better model generating synthetic data just because, right? But I hope you were convinced a bit that we find interesting ways of enforcing these sort of models towards real clinical issues, right? Okay, so now I have some time to talk about quantum. Ideally, I wanted to prepare a presentation explaining, you know, from basics, right, quantum computing. In practice, I finished preparing the presentation yesterday evening, so I kind of improvised things. So the way I'm going to do is to give a very short introduction to quantum computing, to quantum machine learning, and then show you 3 particular projects that we are working on, let's say. Yeah? Okay. So in a nutshell, I guess you have heard that quantum computing is able to, represent data, for example, that is at the same time in 0 and 1 state, or things like that. Yeah, that's just bollocks, no? That's bullshit. Anyway, you can imagine it as a sort of probabilistic method, right? Something where you have a representation of how likely something is in a state 0 or 1. Okay, that would be a probability vector, right? So where you have, for example, 0.8% probability that what you are measuring is in state 0, and 0.2 of being in state 1, right? There are a number of particularities. So one of the things is that these methods work with complex numbers instead of what you're used to, and that has its own motivations in physics and its own, let's say, its own effect on how you work with the data, right? But one of the things is that, okay, so you can represent a state, okay? You can represent a particular state as being in a combination of 0 and 1 in this sense, in the sense of probability, right? So you have an alpha probability of being in 0 and of being in 1, right? How you compute these probabilities is the modulus, well, the absolute value, but these are complex numbers, so the modulus squared would give you the probability of being in 1, and the modulus squared of beta would give you the probability of being in 0 and in 1, right? This is a standard representation of a qubit. Okay, a qubit is a quantum bit, right? And a quantum bit can be represented in that way, right? So not just 0, 1, but actually this sort of distribution. Okay? In non-quantum computing, you have, of course, operations on the data, okay? So if you have some value, right, you can do the NOT operation that goes from 0 to 1, from 1 to 0. You can do the AND operation that if you have 2 inputs, if they are all in 1, that will be 1, and if not, it will be 0, etc., right? In quantum, you have more or less the same sort of things, right? That are based, if you look in this representation, in transformations on this in this sense, right? In the sense of taking into account these intermediate positions, let's say, between 0 and 1, right? So, for example, the poly x operation is a rotation of pi degrees, pi radians, around the x-axis, and it's the same as doing a NOT gate. So if you have a 0, you will go to 1. The Hadamard gate is a particular gate that is very interesting, that basically allows to go from a pure state, from a state, for example, 0, to a state of superposition, a state that is between 0 and 1, okay? It's used a lot in quantum computing. And all these transformations are basically very simple mathematically, because most of this is basically just linear algebra, where you have, in this case, that is only 1 qubit, you would have 2 times 2 rotation matrices that are representing these transformations. Okay? You can see here a bit how they work. The way you work in quantum computing is by this sort of representations, okay? Where you have the input is 0, you have a sort of wire, and this is the operation that you do. For example, here a poly x operation, that would be a NOT gate, right? So from 0 you do 1, from 1 you do 0, or this, for example, from 0 you have a Hadamard gate, that would be a superposition of 0 and 1, right? And like I said before, the probabilities are squared. So you take this, you take the absolute value and you square. That gives you the probability. So basically you have 1/2, 0.5 probability of 0, 0.5 probability of 1. Right? Okay. What else? In the way of working of most people working in this field, you represent operations on quantum bits with these sort of diagrams, okay? Like we saw before, boxes with wires, or here, these sort of operations, right? So this would be a controlled NOT gate that does a NOT operation only if this qubit is in 1, right? But you can see that, that there is a very, very big difference between what we were seeing before and we see now, yeah? And that is that the level at which the research is happening in quantum computing is a much, much more basic level than what's happening in classical computing, okay? Because the technology and everything is also in a very, very, very early stage, right? So these sort of things you do when you're analyzing microprocessors and things like that in classical computing, right? Not when you're doing big algorithms of machine learning normally, right? Okay. Now, yeah, what is interesting is that this would be for 1 qubit. If you take a set of qubits, okay, so here would be a qubit in 0, qubit in 0, qubit in 0. You can imagine it as a set of wires when you have many wires like this in parallel. You can represent information in exploiting this idea of the superposition of states, okay? And that's where the kind of punchline of quantum computing comes. Because when you have, in this case, for example, with binary information, with n qubits, you are able to store 2 to the n values, right? And that has a lot of potential, right? Because 2 to the n, for example, if you have 100 qubits, you can represent an amazing amount. You can do the calculation of information far, far bigger than anything that you can reach with any supercomputing nowadays, right? So that's one thing that is that is powerful. The other concept is the one of entanglement that, again, popular science is selling us as things that are very amazing. But basically, the mathematical definition of entanglement is that when you have these sort of superposition states, you can represent them as combinations, as a tensor product of different elements, right? So, for example, this value here, okay, which would be 0, 0 with a probability of this, 0, 1 with a probability of this squared, all that, right? This can be decomposed as 2 qubits, right? One in this state and one in this one, okay? That's a product state. That is not an entangled state. But for example, this one, you cannot decompose, okay? It's impossible. You can do the maths, and it's impossible. And that has a number of things that allow for more powerful computation. Okay? Right, and how do you generate this sort of entangled states? Well, there are a number of basic operations, but the basic building block is the Hadamard and CNOT gates. That's used a lot to generate these standard entangled states that are called the Bell states and are famous. And, well, these people got the Nobel Prize for something related to this. Anyway, in a very, very, very basic instance, I showed you what is quantum computing, but I want to jump to what is quantum machine learning, okay? And there's a small taxonomy of what is meant by quantum machine learning, okay? This is a very recent discipline. It happened from just a few years ago, and it has been growing very well, okay? So one possibility is you have non-quantum data, so classical data, and you have a classical algorithm, okay? Is that quantum computing? Well, in theory, no. That's a standard, classical computing, right? But not only that, right? There is a whole family of methods that use classical data and classical hardware, classical algorithms, but are based on mathematical formulations of quantum mechanics. This is what is called quantum-inspired computing. And that's a direction that's very interesting, because it's a direction where there is a whole community of people from physics that are locked in their labs, and probably they don't talk that much with computer scientists, right? And maybe the methods they use have a potential to develop new machine learning methods, right? Without any quantum hardware or whatever. And we will see an example of this in the third example that I will show. Okay. There's the other extreme where you have quantum data. What I mean by quantum data is, for example, or typically, data from physics experiments, right? If you work in CERN and you do things with the Large Hadron Collider and things like that, you can have quantum states where you want to do quantum tomography. You want to do some sort of characterization of this, right? And you could use a quantum computer for this. You could do quantum algorithms. But this is a very particular discipline, and it's not so developed, and it's not something where I'm working on. It's more people at CERN and things like that, right? Then there's the other way around. So when you have data, again, from physics experiments or whatever, but you use standard machine learning to analyze this data, this, again, is a very big community, but it's just, let's say, an application of existing machine learning methods, right? But then there's this one where we are mostly working, where you have classical data, you have a standard thing, you have images, you have data from patients, whatever, and you want to devise quantum algorithms, okay, or to leverage quantum hardware as well to be able to analyze this data. Right. So I will show a few examples of things that we've been playing with, right? One is this one that is work that was started by Lois Riobot and continued by Xavi Font-Aragonés, right? It's based also on the same type of data that we were using for the lung example that I showed before, so lung nodule progression, lung cancer, right? And I will show a bit some of this. So this is taken from a presentation of Lois, so some of the motivation may be repeated from what I just said. But basically, yeah, so quantum computing is promising, whatever, right? But it's promising at a level where typically quantum computing people are saying that we are more or less at the stage that classical computing was in the 60s or 50s, right? So if you want something that has a big effect now, immediately, work on something else, right? And that's part of the motivation why I jump on this, right? Because I wanted also to have a research line that is more like slow science, focus on the methods, on the maths, and if I publish something in 2 years, it's okay, right? Instead of running behind all the deep learning last trends, right? Which I do anyway. So. Okay, so the objectives, yeah, to explore the potential of quantum machine learning methods to solve, in this case, image classification problems, but we will see also for image generation, and to design and execute different algorithms, understand current limitations, and basically to create a sort of benchmark of different methods also for the community, right? Again, what we said about quantum computing, this is a picture of a quantum computer from IBM, right? Where they have the chip here. It has to work at super low temperatures because it has to keep access to this sort of quantum behaviors without interference. But there are a number of technologies, like photonic technologies and trapped ions and other things to implement quantum computers. This I kind of said already, okay? Superposition, entanglement, right? And these are the sort of operations that I was saying. So for example, if you have an X gate, a poly X gate, which would implement a NOT, so going from 0 to 1, or a Hadamard gate that instead of going from 0 to 1, it kind of flips it on the horizontal plane, right, which would be this superposition. You have rotation gates, the identity gate, of course, that does nothing. And something that is very interesting is the measurement, right? And the measurement was also pictured here. The qubit can be in a superposition of many states, and like I said, you can represent a lot of information with few qubits. But when you do a measurement, it's a projective operation. So basically, you measure just one value, right? So it can be there can be a lot of probabilities that it can be in 0, 1, whatever. But when you measure 0 or 1, right? So you don't measure anything else. And if you want to have access to these amplitudes, these values that you store, you have to do it statistically. You have to sample many times, right? And then reconstruct how many times it appeared 0, how many times 1, to get these values that you stored. So one of the main limitations is first of all, how you encode the information. If you have classical information, how you put it into a quantum computer. That is something that is very costly, right? So sometimes the advantage that you may have with the quantum algorithm doesn't compensate all the effort that it takes to load the data. Then you do all these quantum operations that can be in parallel. So you can, for example, apply one of these operations in parallel to this superposition state. So basically, you're applying one operation to all the possibilities of values at the same time, which is this concept of superparallelism. But then again, when you measure, you only get one value. So you have to repeat many times the same thing. And that also can be a limitation. Apart from other limitations of quantum computer, like not being able to copy a quantum state, right? So there's the non-cloning theorem. That are things that are kind of given for granted in classical computing, but in quantum you cannot do, right? Okay. So this is kind of the type of diagrams that we work with, like we showed before. So things where you have different qubits, in this case 3 qubits, and you do a multi-qubit operation. In this case, it's what is called a Toffoli gate that is controlled by 2 qubits to do an operation, a NOT gate, a rotation, a Hadamard, whatever. There's something called the swap gate here that swaps information from one qubit to the other. And with this sort of puzzle, you make your operations, okay? That's how you design algorithms in this way. I was saying that before, this is one of the ways of working on quantum computing. That is the quantum circuit paradigm. There are other ones. For example, I know people here in the Barcelona area that work on adiabatic quantum computing. That is more, let's say, taking the perspective of how the data evolves, right? And I don't want to say something too rushed about this because it would take time to properly introduce it. But basically, it's based on working on a Hamiltonian evolution, so working very much on the physics aspect of how the state of a system evolves with time, and then you kind of work on designing this Hamiltonian matrix to then get the data from the initial state to the final state that you want. So they work at different type of conceptual levels. So like I said before, the basic elements of any quantum machine learning algorithm would be encoding the data. So you have classical data that you want to, let's say, upload into a quantum computer, and you want to put it in a way that the values are stored in this superposition of states, right? And there are different ways of doing this. There's the algorithm itself, right, that processes the data, and there are a number of architectures. Mostly, people working on machine learning in the quantum realm, they use parameterized quantum transformations. So you can imagine that you do some operations, and these operations, they depend on some values, right? And you basically run the whole algorithm, get an output, okay? And then do a classical optimization acting on these parameters. So basically, you're tuning the parameters the same way as you're tuning the parameters of a neural network by running these many times and doing a classical optimization. And finally, there's the last part of the measurement that I said here. That gives the output, and then you're using, and then you have to repeat this many times to get the information. Okay. For biomedical applications, there are some people working on that, right? most of them, or the most, let's say, successful ones, are based on quantum annealers. So quantum annealers are a specific type of device. Okay? So typically, quantum computers, the state of the art nowadays, I think that the highest number of qubits is probably people from IBM. They have this roadmap that is super interesting, that is proposing how they will grow in number of qubits. But I think that there's one that has 127 qubits, and I think they were about to launch something with 200 and something. But yeah, it's the range of where we are. And these are physical qubits, right? The difference between physical qubits and logical qubits is that these are noisy qubits. And to implement a logical qubit, you need many physical qubits to make sure that you compensate for noise, that you allow for connectivity, etc. Anyway, so quantum annealers are a very specific device for a very specific problem that is basically binary optimization, combinatorial optimization. You have a set of 0 and 1s, and you want to find what is the right combination of these values for a particular problem. Within something that is called Kubo problems, so quadratic and constrained binary optimization problems that have a particular formulation. So if your problem fits perfectly into this formulation, you can buy a computer from D-Wave, that's a big company in Canada, with like 5,000 qubits. That's okay. But only for that, right? So that's what quantum annealers are. So anyway, we wanted to start working on quantum machine learning for image analysis. So the first thing that we looked was, okay, how do we encode the information of an image into a quantum computer? Okay, we had these 3 steps, so how to work on the first part. And there are a number of algorithms, and I will show an example of one of them, of the NEQR, right? There is some promising initial work on quantum algorithms for image processing, like edge detection and things like that. So we wanted to analyze a bit how they work, right? And for classification problems, okay, that there are some methods, but basically it was all very initial and mostly applied to data like MNIST, things like that. And we wanted to see for more, let's say, realistic data. Okay. There is also, like in machine learning, there is a lot of fuss and buzz and fireworks on this, right? So people claim a lot of things that are a bit inflated, right? So one of them, for example, is that some people claim that they work on big imaging data, medical data, etc., right? But the first thing they do is take the images and do a very aggressive dimensionality reduction. You take the input, you pass it through a PCA, and you get only like 5 values, right? And then you do your quantum computing with that. And they say, okay, we work on high-resolution data, but in the end, they work on a vector of 5, so it's not. So we wanted to see, okay, how realistically we could approach these sort of problems, right? Okay. So yeah, we took data from the same problem that we saw for the thesis of Xavi Rafael, except that, well, we focused only on the nodules, and on top of that, instead of 3D, we focused only on a cut. So we're working on 32 times 32 images, which is a bit of a joke for machine learning, but for this type of work is kind of state of the art, right? Okay, so that's a bit the data set that we had. So then automatic identification of regions was given already from the thesis of Xavi Rafael, classically. So we have this automatic identification, we take a slice, and well, we had a training set, test set, etc. And this study in particular was using something called Qiskit, okay? Qiskit is a toolbox that is provided by IBM. And that's something that I want to mention also. This community, the whole community of quantum computing and quantum machine learning is very open. And there is a lot of sharing of stuff. So IBM shares not only the toolkit, but actually the hardware. So you can run on their quantum computers things directly. But there's IBM, there's Google has Circ. There's a company in Canada called Xanadu that has a toolkit called PennyLane for quantum machine learning, that again, everything is open, they have examples, they have kind of an internet textbook where you can learn quantum computing, and they have better explanations than what I did. But basically, well, we work on this type of framework, taking the images, comparing a bit direct image encoding approaches, like this FRQI and NQR, versus things like I was mentioning before, so taking the image and doing dimensionality reduction, either by PCA or an autoencoder or whatever. to then do a feature map to encode this and end up with a representation of this image in 10 or maximum 20 qubits. Okay, this is for the data embedding. I will jump, right? This is an illustration of what I meant by this INIQR circuit, right? That is taking into account already that images have a certain structure, that they have positions, intensity values, etc. And it's a specific way of encoding that reduces the number of necessary qubits to encode an image, right? That's a bit the general idea. Okay. And then once we have the information encoded in quantum in qubits, we pass it to different classifiers, right? And there are different architectures of classifiers. The ones that we were using in this study are basically methods that were already available in Qiskit, but of course we're working on new methods as well. And what I said, yeah, so you run through it, you do an output measurement, 0 or 1, you compute with the ground truth, and this is classical, so the green is classical, the blue is quantum. And these loss functions updated to then update the parameters of the ansatz, of the method that has some parameters. Right? This is an example of an architecture for a classifier, okay? It's very much like a neural network, so you have different repetitions of layers, right? Where you combine a number of parameterized unitary operations, so operations that have a parameter that you're optimizing through the loop, with entangling gates that work the magic a bit on being able to have more power with few qubits. Okay. Right, we did a comparison. One of the things, we were working only on simulators, so we did something on real hardware, but not the full study. So on simulators, of course, things take a lot of time, yeah, compared to the classical algorithm, which was much faster and also better. No? But well, it's a way of starting working in this field and continuing on this, right? And that's a bit the general conclusions, okay? I will jump for the last part a bit more quickly. There's a second part that is more focused on generative models, I mentioned, okay? So this part of the work that Natalia is doing, who is sitting somewhere there, okay? On analyzing different algorithms of quantum machine learning that are focused on generative models, okay? So this is classical motivation. We basically want to do that, yeah, analyze different algorithms, right? So there's something wrong with the text. I don't know, it went a bit strange when I passed it to this computer. But one of the architectures that is being analyzed, and I will take it to explain a bit more in detail how it works, is something called patchgan. Yeah, it's a method that was published there in 21 by some guys. And it has like two types of architectures, what is called patchgan and batchgan, depending on how many qubits you have, right? So the overall general idea is when you have an image, and in this case they were working with MNIST, if you have very few qubits, you can split it into patches and then do a quantum circuit for each patch, right? Or if you have a lot of qubits, you can even pull together different images to do like a mini batch and do optimization there. Okay. In this case, this is a GAN type of architecture. So you have a generator and a discriminator. In this particular algorithm, the discriminator is classical, so there's nothing special there. But the generator is quantum, right? The paper is based on what I said about patch and batch, right? Okay. So the quantum generator, like I said, for the patch strategy, is based on taking the image and splitting into different images. Okay, it's based on an architecture that is like a quantum neural network. Basically, it has a set of layers, right? And each layer is composed of these sort of gates, right? So C0 gates, that parameterized rotation gates, etc. Go fast because I know I'm running out of time. This is a bit the calculations that you do for the number of qubits that you need. Okay, so if your data has a dimension 2 to the power of this ng, you will need ng qubits, right? But on top of that, to be able to have more representation power, you need to be able to do some operations that are nonlinear, and you do this by what is known as ancillary qubits, that are extra qubits that are added to then be able to have more processing power, let's say, on the data, right? Okay, so this would be the qubits that are used to represent your data. So your data, you upload it, let's say, you encode it in this first part, right? you have these ancillary qubits that are used as resources for later processing. And then you repeat L times different layers. And then at the end, you have measurements as usual. Okay. Yeah, this is the part that I was saying for the layer. The nonlinearity, I pass quick, yeah, so to finish. And you see here that the loss function of the overall method is pretty much a GAN loss function. So something that is putting into play the loss of the discriminator acting on data generated by the generator. So in theory, you want that the discriminator is good at discriminating what is real and what is fake, yeah? And at the same time, well, some other losses that are typical for GAN. Okay. This is just screenshots of the implementation in code of how Natalia is working, right? So how these things. So there are a number of libraries where you can work on these rotation gates, CNOT gates, etc., right? And they allow to implement all these transformations. And the batch strategy, I go very fast, yeah, whatever, basically, in this case. Right, so on top of this method, the basic method, we're also looking at other versions. So what we saw is that the patch GAN was not particularly stable. In fact, the data that it generates is quite crap. And by adding a Wasserstein penalty term, like in a classical GAN, it allows to generate better results. There are other methods like this one. This paper that is quite recent also is from 2024. That had like two different variants, so a quantum variational circuit or a neural network layer for the generator, and then a classical discriminator. We're also starting to work, but we still don't have the results on very early attempts of implementing diffusion models with quantum circuits. Okay? And here, well, we have a first implementation from some collaborators that recently published a paper in 23, and we're starting to see how it works with clinical data. And also, we're starting to work on other type of applications, like, for example, for ECG data, where there was a recent paper as well. Okay, so the work this project is going is there's a lot of work of getting all this to work, modifying the methods, testing on the data, proposing metrics, like, for example, the realism of the images that are being generated, the accuracy, if there's some classification, but also metrics related to quantum, so qubit resources or any sort of other, oh, wow, what happened to the text here? And these are the databases that Natalia is using. Yeah? So the blood images from Medemnist, and data from BRATS, that's a brain imaging data set for brain tumors, except that, of course, we have to subsample and we have to reduce the size of the images for some of the algorithms because it's impossible to get as many resources to work, right? And that's a bit the current state of this project, okay? And then the final one that I will go fast also, is work that I'm doing in collaboration with CERN and with Barcelona Supercomputing Center, okay? And it falls in the category of what I said before, that classical is also something in quantum, okay? So these are quantum-inspired machine learning, what is called, right? So methods that are based on mathematical tools that are used in quantum physics, right? That maybe are not so much exploited in classical, let's say, machine learning, right? So that's work of the PhD thesis of Emma, right? What is the particular formulation or the particular method that is plotted here is what is known as tensor networks, okay? Tensor networks, they come from the field of physics, and they're used to represent, for example, quantum data, where you have a very high dimensionality, but you want to be able to efficiently work with this data without having like huge matrices, right? And you can see it a bit like as a dimensionality reduction type of method, basically, right? So you can represent, well, what they mean by tensor networks, okay? So a tensor can be, well, a 0 tensor is just a scalar, a 1 tensor is a tensor of 1 dimension, so a vector, a 2 tensor is a matrix, a 3 tensor would be 3 dimensions, you get the idea, right? And there's a whole field that works with this type of representations, okay? And this type of representations are exactly as accurate as if you use the formulas, right? And you can see these guys drawing circles and lines and things like crazy, right? And they are doing mathematical operations that are super amazing, right? So the basic operation is what is known as tensor contraction. So for example, here, if you represent this operation where you have a matrix multiplied by a vector, okay? So you have a 2 tensor here because it has 2 legs, right? I and j, 2 indices. And you have a vector here because it has only 1 leg, so it's vi, right? And tensor contraction would be converting this into just 1, which, as you know, is a vector. Okay? That's a bit the overall idea. And then this works on, iteratively on doing the contractions, calculations, optimizations, etc. And that's a bit also other things that you would see in this type of works, right? So the operation of a transpose of a matrix is represented like this, or the trace of a matrix like this, eigen decomposition if you have a matrix and do this, singular variable decomposition, etc. Right? There were some early works. In fact, we only found one work of somebody that tried to apply tensor networks to medical imaging. And this is people from the University of Copenhagen that developed a method for image classification, and also they have some follow-up work for segmentation. Okay, that were representing the image as this type of representations, yeah, in what is known as an MPS, a matrix product state, that is a type of tensor networks that is easy to manipulate, let's say. And you can see here that they have these sort of contraction operations that reduce the size until they get the final result. They have a hierarchical type of thing where they have the initial image, they reduce, etc., until they have a final smaller resolution. So it will be like the pooling in a neural network. Right? And the work that we're doing with Emma, and we recently submitted something on this, is using this same thing as MPS, as the people from Copenhagen are doing, but combined with something that is called SMPO. It's a different type of tensor network. And the idea of this algorithm is to have 2 parts. One that is fully unsupervised, where we are working with the Lang nodule data. And what we do is we input the Lang nodule data, we train this, and all this part is unsupervised in the sense that what we want is anomaly detection. So we want to train a model, and if you have a new image, if it's too far to the distribution of the data that you gave, it will kind of give an alert, okay? And then what we do is we combine this with a semi-supervised. So we combine this with a standard, let's say, MPS, but with very, very little annotated data. So the idea where you have a big database of images, but only a few of them are annotated, but you want to exploit all the data for the training. And again, this is very recent, and we will have some. But basically, what I showed you, so I showed you about why I think that generative models are something in medical imaging, even though many people are jumping on it. The particular example of the work of Iram, right, with these variational autoencoders, A3VAE. The particular work of Xavi Rafael with his prediction of the evolution of lung cancers. And the work of Mireia also on building models of brain growth, let's say, right? And then I showed you also 3 small examples, one for medical image classification applied to lung nodule images, okay, with Lois and Xavi. The work here on the quantum generative models, where we're doing a bit of a benchmark, let's say. And the idea of this, and this is why, for example, in this work, Artur, who is the head of the quantum group in Barcelona Supercomputing Center, is also involved. The idea is to scale this to really a resource that is open to the general community, where they can test different algorithms, being able to implement it also in Mare Nostrum in the sense that we can simulate a high number of qubits, so to bring it closer to images of a reasonable size, etc. And the final example that I showed in collaboration with CERN and BSC also. And that's it. So, thank you.